We're going to go ahead and get started in lesson 5. And lesson 5, we're going to be looking at 4 different concepts. This first concept, we're going to be looking at exponents and radicals, and just how to work with exponents and radicals and kind of how they work together. So hopefully your understanding will be a lot better, and this is really not that tough. Looking at it here, this first example, of course, we're looking at lesson 5 on page 43. The first example right here, we see root x cubed y, and then we see the fourth root of xy cubed. Now, the first thing you're going to do whenever you're going to see radicals, exponents like this, is you're going to substitute, instead of the radical, we're going to put parentheses on both of these. And whenever you do that, you still have your x cubed, your y, your x, your y, your cubed. But if you'll notice, this is the square root of x cubed y. How do we know it's the square root? Well, it doesn't have a number indicated, so it's automatically known, implied that it's square root. Over here, you have, looks like square root, but you see a 4 right above the radical. Well, that means the fourth root. And another way to write square root is to write it as a radical, or write it as an exponent. So this would be to the 1/2 power because it was square root. And this will be to the 1/4 power because it's the fourth root. It's just another way to write it instead of having the radicals there. What you have here now is you have parentheses to a 1/2 power. So what we have is we have x cubed to the 1/2 power. So we have a power to a power. It's called the power rule. Anytime you have a power to a power, you multiply the exponents. Now before, what we have had is we have had something like x1 times x2. And this is base times a base. You add their exponents. It's called the product rule because you're multiplying the bases. You get the product of x times x. Well, what you're doing is you're adding the exponents. So it would be x cubed. Because anytime you have a number times set, you add the exponent. What we're going to do here is called the power rule, and when you have power to a power, you're going to multiply. So x cubed to the 1/2 power, you're going to get x to the 3/2, and this is y to the implied 1, so you're going to get y to the 1/2. Right here, implied 1, you have x to the 1/4, and then you have y to the 3/4 power, because you're multiplying. Easy last step, you're simplifying, it's back to the product rule. Up here was the power rule, power to a power, right here's the product rule. So x times x, you're going to add the exponents. So 3/2 plus 1/4 is going to be x to the, well obviously you got to change this to fourths, so you multiply it times 2/2, so it'd be 6/4, so we get common denominators. So you get 6/7/4, can't get any more simple than that, so that is as simple as it can be. And then you have y to the same thing. We're going to move this to 2/4. You get y to the 5/4. So there's your answer right there. Look at this next one. Same thing, same rules. This time there's no radicals that I have to move. It's already to the power. So we bring our a to the x/2 down. And then we're going to distribute, because the 2 minus x, these powers can't be added, we're going to distribute the 1/2 to both. So you get y to the 2 times 1/2 is 1, and then you get minus x/2, or 1/2 x, same thing. All over x cubed, a3x, y negative 2x. Bring everything to the top. Whenever you bring things to the top, you're going to change the signs. So you get a to the negative 3x, and you get y to the positive 2x. And then the last step is just going to be to add the like bases. Or add the exponents as you multiply the bases. So a times a, you add their bases. So this is 1/2 x, negative 3x, and so that's going to be negative 2.5, which is negative 5/2 x. So we have a to the negative 5/2 x. I guess that x technically needs to look a little better like it's on the top. And then you have y to the, and the x's, so you have 2x minus 1/2 x, you get 1.5 x, or 3/2 x. So y plus 3/2 x. And so you understand everything here. It's just adding the power to a power where you have to multiply. We'll look at a couple more of these. 3 more problems with this first concept. Look at this first one here. And the first thing you're going to do is you're going to make all of the negative radicals positive. And because there is an addition happening, this is the first time we've had this plus sign up there, changes the way we do things. We can't just bring the x down and the y down and bring this up like we want to because of the addition sign happening. So we have separate terms. We've never had that when we've been dealing with these. The first thing we're going to do is we're going to make this 1 over x squared plus 1 over y squared all over 1 over x, y. And so that got everything kind of how it needed to be done. What we're going to get now is common denominators up on the top. So multiply this times y squared over y squared and x squared over x squared. Now we have common denominators of y squared plus x squared. So what's going to look like is y squared plus x squared over x squared y squared over 1 over xy. Last step we're going to do is we're going to flip this and bring it to the top. So x over y over 1, and then x, y over 1. So this is a multiplication happening up top. Bottom is gone because we flipped it and brought it up. Now what you can do is you can cancel one of these x's and one of these y's and that and that. So our answer is y squared plus x squared all over x, y. So that was a simplification of what we had up here. So just using the radicals and manipulating them how we want to. Looking at the next one, we have radicals here, and what we're going to use is we're going to get common radicals so we can add them. And the way we're going to do that first is we're going to simplify some things. And the first rule that you got to know is you can't have a radical in the denominator. So we're going to make this look a little different. So we have 3 root 3 over root 2. We didn't change anything. We just made it look a little different. And then we're going to have minus 4 root 2 over root 3 plus 2 root 24. First thing we're going to do is going to get the radicals out of the denominator. You can't do that. So we've got to change it. So you're going to multiply this times root 2 over root 2. The reason we chose root 2 is because we need the same radicals in the denominator, and because any radical times itself is itself. Root 2 times root 2 is 2. So what we've done is we have gotten rid of the radical in the denominator. Now up top, you have 3 root 6 left over. Now minus, you're going to multiply this one times root 3 over root 3. So what we have is 4 root 6 over 3. Once again, we got rid of the denominator. And we're going to break down radical 24. We've done this in class. We have 2, 12, 2, 6, 2, 3. What we did was we got it down to its prime factors. So what we have is we have root 2, root 2, root 2, and root 3. Any radical times itself is itself. So the pair of 2's come out, and that 2 can multiply times that 2. So what you end up with is you end up with plus 4 root 6, because these guys are still left inside there. And you'll notice we have root 6, root 6, root 6. Now, if we'll get common denominators, we can now add these. Of course, the common denominator is 6. So multiply this times 3 over 3 to get 6. Multiply this times 2 over 2 to get 6. We'll multiply this times 6 over 6 to get 6 on the denominator. So 3 times 3 is 9 root 6 all over 6. Minus 2 times 4 is 8 root 6 all over 6. Plus 24 root 6 all over 6. So now we have common denominators and like radicals. We can add the numbers in front. So we have positive 9, negative 8, positive 24. 24 plus 9 is 33. 33 minus 8 is 25. So we have 25 root 6 over 6. The last thing we're going to look at is can we reduce the 25 into 6? And the answer is no. So that will be our answer to this problem. Last one on the radicals here. All we're going to do is we're going to distribute and do the double, I call it the double distributive property, which means we're doing the distributive property twice. So we'll take the root 2 and distribute it here 2 times. So root 2 times 1 is root 2. Root 2 times negative root x is going to be negative root 2x. So that one is done. So now we go root x times 1, so we get plus root x. Then we do root x, positive root x times negative root x is going to be negative x, because any radical times itself is itself. And so what we'll have here is nothing can be added together. So this actually will be our answer, this big complex thing, because there are no like radicals. So you leave it like that. The second concept we're going to look at in lesson 5 is complex numbers. What is a complex number? A complex number is, it's an imaginary number. An imaginary number is something that can't be graphed on the number line. When you look at complex numbers, we know them as imaginary numbers as i's. And here is the I chart that you need to write down on your formula page so you can remember it. And there's really only 4 that you have to look at. The first one is root negative 1. Anytime you have a radical in the, negative in the radical, it's actually an imaginary number. You can't graph root negative 1. And so root negative 1 actually becomes root 1i. That negative sign comes out and it becomes an I, which is symbolic for imaginary number. And the root of 1 is just plain 1. So we end up just getting I. So root negative 1 is simply I. Root negative 1 times root negative 1 is I squared, or negative 1. And obviously, any radical times itself is itself, so you see that that rule is still in effect there. But anytime you see I squared, you can just automatically write down negative 1. You have root negative 1 times root negative 1 times root negative 1. You have 3 of those. You have I cubed, and I cubed is negative I, which makes sense because I cubed is basically I times I squared. Right? That gives you 3 i's. So you get negative 1 times I, or negative I. So it makes sense how a pair of these come out to make negative 1, and the one that's left over is the I. So you can kind of get your understanding there. The last one is negative 1 times root negative 1 times root negative 1 times root negative 1, which is 4 i's. And so 4 i's is the same thing as I squared. So I to the 4th is the same thing as I squared. If you had I squared times I squared, you'd have negative 1 times negative 1, which is positive 1. So it kind of makes sense how all this works out. Then, after that, if you have I fifth, they all repeat. So if you have I squared, I cubed, I to the 4th, I to the 5th would just be I. Because every 4 is always going to give you a 1. So you almost subtract 4 from each of them. So you have I5, subtract 4 from it, because it's always just going to be a 1. What's left over is just I. So I fifth is this, I6, I7, I8, I9, I10, 11, 12, 13, 14. It just repeats over and over and over again. So you just take all the 4's out. So if you get I to the 13th, you take out 4 is 9, take out 4 is 5, take out 4 is 1, because all the 4's always equal to 1. And so then you would have just 1 I, it would just be I. That's how all of those simplify down. Let's look at one and do these. Not too complicated if you memorize your chart. So I cubed, what we'll do is put parentheses, and in place of I cubed, we're going to put negative I. Plus 2, I to the 5th. Remember, every 4 it repeats. So take 4 off of this, you're just left with I. Minus 3I plus 2, what is I squared? I squared is negative 1. So now we really made it simple. So right here you have negative 3I plus 2I minus 3I minus 2. And then you treat them as like terms. So you can add all the i's together, and then you can add all the constants together. So we have negative 2, and we have negative 3i. Negative 3i is negative 6i. Negative 6i plus 2i is going to be negative 4i. And that's how you would write it. You write the i's second, and you write just the normal numbers first right there. We'll look at one more example, then we'll move on to the third concept. This is another type that you guys will come across where you just have radicals, there's no i's in there. You got to take the negative that's in the radical and make it an I. So what you're going to have here is 4 is a perfect square. So this is going to be root 3i, because the negative came out of the radical. This is just going to be 2 plus 3 parentheses root 2i. And this is going to be, since 9 is a perfect square, it'll be 3i because the negative came out. This will be plus 4i plus 4. Do one more multiplication. We have 2 root 3i plus we have 9 root 2i squared plus 4i plus 4. Now we'll add the like terms together. We'll get, well, really, there's no like terms, so we'll have 4, and this is the way to write this in descending order. 4 plus 4i, and then we're going to have, I guess properly, if we were writing this the correct way, it's not wrong, it's just the correct way to write it. Because this is I squared, I squared is going to end up being negative 1. So we're going to have negative 9 root 2i. No, it's gone, sorry. It's just negative 9 root 2, because I squared came right here and made it negative. Then we'll have plus 4i, then we'll have plus 2 root 3i. So once again, in this one, much like the one we had earlier in the top right-hand corner, nothing was able to be added together. So it stays pretty complex like this. Not a lot of math to be done, so just simplified it a little bit. You're going to like this one. This is a pretty easy concept for the third concept. And in order to really kind of understand this one, you really need to look at page 45. And you need to look at 5.C, the first example 5.8, and kind of follow along to make sure, because it's a word problem, so you got to learn to draw this out. But I just wrote down what was necessary. It says the scale factor of 2 rectangles is 4. And it says, what is the ratio of their areas? Well, they didn't give us anything other than that, but if you draw a mental picture, you have 2 triangles, and their scale factor is 4. Which means that one of them is smaller, one of them is larger. So it's 4 to 1. Even though it doesn't say it, it's implied that it's 4 to 1 or 4 over 1. That's their scale factor. And so what's the ratio of the areas? Well, the ratio is 4 to 1 of what it is already. And it doesn't even tell us which one is to go first. So you would be right either way that you did it. But if the scale factor is 4 to 1, what are their areas? Well, if it is, and it says, it does say 2 rectangles, but it says the scale factor is actually a square. If it's 4 to 1, it means all of them, it'd be 1, 1, 1, 4, 4, 4, as far as how much larger they are. So it would be 1 times 1 and 4 times 4. So basically, when you're doing this, you would multiply times itself, because that's the area is base times height. So the ratio from one to another would be 16 to 1 or 1 to 16. So these are not really tough at all. You hope you see these in the homework. It wouldn't matter what it is. It's exactly how you would go about finding the answer to this one. And now to the fourth concept. Remind me in class of the fourth concept as I'm looking at this. I want to do this one with you guys in class because I want to show you kind of a visual of what this is. So basically, you're just going to do the Pythagorean theorem twice in order to solve for these. You can look in the book and figure it out on your own, or this next Monday or Tuesday, I will help you guys. So remind me in class, and I'll help you with this one. Won't take very long. I want to do a visual aid of a Kleenex box, and we'll learn how to solve this. But the math isn't super hard at all. You just take Pythagorean theorem, you're finding the hypotenuse twice, and then you will have your answer to the diagonal of this one. So that's it for lesson 5. Not too tough at all.